Today we're going to be covering refraction, and this is for GCSE refraction, but it is also applicable to A-level. So let's get started. So here I've got my light ray coming in, and I'm going to denote my light ray's direction with an arrow, like this. I'm also going to draw on and label my normal line. Now my normal line is the imaginary line that is perpendicular to the surface. We sometimes just call it the normal, or sometimes the normal line. By perpendicular, I mean it forms a right angle here. So first, to think about refraction, we have to think about what the refractive index is. The refractive index, n, is, let's label it, the refractive index, n, is the ratio of how fast your wave travels relative to how it would travel if it was light in a vacuum or if it was sound in air. So we define it by the ratio of the speed of light to the speed that you're traveling in. So I can label c as my speed of light, and this is my speed in the medium. What do I mean by medium? By medium, I just mean a substance, either air or glass or water. So let's label this as n air, and we know the refractive index of air is simply 1. So let's have a little look at our refractive index equation a little bit deeper. So let's test this equation out. Let's say in medium, let's say that my speed v in some medium is equal to 1/2 the speed of light. Let's say that I slow down by a factor of 2 when I enter a new medium. Then my refractive index n will be c divided by 1/2 c. The c's cancel out and the 2 gets flipped because it's on the bottom, and you end up with a refractive index of 2. This means that my speed of the light slows down by a factor of 2. Okay, so it slows down by a factor of 2. Then let's draw some lines and construct a diagram of what this might look like. So if I have n air equals 1, and I'm going to say n, we're going to go into some glass, and this is the one that you'll do in school, and I'm going to say my refractive index of glass is 1.5. So we know the light slows down in glass, and because it slows down, it changes direction. So my light ray comes in and enters the glass, and actually it changes direction. So my angle, let's pick another color, my angle, let's do the angles in pink. My angle here, theta I, the incident angle, and my angle here, theta R, refracted angle. We can see that the light ray has bent towards this imaginary normal line, this red dotted line, when the light has slowed down. So to demonstrate this, I'm going to draw a little car here with 4 wheels. Now, you can imagine this car going along on the tarmac, if this is the tarmac or the road, and the car hits some mud. Then this wheel here, this first wheel is going to hit the mud first. If it hits the mud first, then that wheel is going to slow down, but you have to remember that these other 3 wheels are on the road still, so they're still spinning really fast. So the entire car gets pulled round. So that is how I remember which way the light bends. So if you're going from a low refractive index into a high refractive index, then it's like going from the road to some mud, and the car gets pulled round because this first wheel hits the mud first. The same for when you're going from the mud outwards. then you're going from the mud outwards. This wheel here is going to hit the tarmac first, and it's going to pull the car back round and away from the normal. So slightly confusing to see perhaps when I draw it, but hopefully that makes sense. So we end up with a law, and this law is called Snell's law. Snell's law states that the refractive index of medium 1 times the sine of the incident angle is equal to the refractive index of medium 2 times the sine of the refracted angle. And so this is our important formula to calculate either the angles or the refractive indexes of the medium.